So today's lesson is about differentiation again, but this time the chain rule. So we're going to look at what the chain rule is and what sort of situations we apply the chain rule. First of all, we can differentiate this function and we can differentiate this function. What we currently can't do is differentiate the composite function. The chain rule is something we can use to differentiate these kind of functions. But before we actually look at the chain rule, I'd like us to go back and look at composite functions so that we can fully understand the chain rule. This is a function machine. It's a visual representation of what happens when we carry out a function. So we put some value x into the function f of x, and out of it we get the solution f of x. We put x into the function g of x, and out comes the solution g of x. So we're going to use the function machines to see what happens when we carry out the function g dot f, which, if we remember, is g of f of x. So we put x into the top of the function machine, and out comes f of x. F of x then goes into g of x, and we end up with there's a mistake here. That should say g of f of x that's come out of the bottom function machine. To make explaining the chain rule a little bit easier, we're going to look at this in terms of shapes. So I put a circle into the top of f of x, a square comes out, I put the square into g of x, and a triangle comes out. So what does this have to do with the chain rule? Looking at the shapes, if we want to decompose the composite function d triangle with respect to the circle, we would do it in this way: d triangle over d square multiplied by d square over d circle. So this works for the chain rule. We can write dy by dx equals dy by du over du by dx. U is just something we use as a mechanism to explain this. Another way of looking at this is if we look at y equals g dot f, then that's g of f of x. So dy by dx is d by dx of g of f of x. Now if we consider this as two functions, an inside function and an outside function, then what the chain rule tells us is that we need to differentiate the outside function but keep the inside function in it intact, and then differentiate the inside function and multiply those two results together. We have two ways of writing the chain rule. Dy by dx equals dy by du times du by dx, and this is the Leibniz notation, or the function notation version, which I've just explained to you. Put it in a blue box because it's important. Another thing we can do with the chain rule is write a rule for deriving b to the power x. So this only works when b is greater than 0 and not equal to 1. So what we need to do is recall from logarithms that b to the power log base bx equals x. If we set b equal to e, then e log e x equals x. We could also write that e to the power x natural log b is equal to e to the power natural log multiplied by b to the power x. B to the power x has become the x in this case, and so that is equal to bx. We're going to take these two bits up here and we're going to apply the chain rule to them. We're going to say that a composite function of e to the power x and x log b. So when we carry out the chain rule, we end up with e to the power x log b multiplied by log b. We've already said that e to the power x log b is b to the power x, so we can write that the differential of b to the power x is b to the power x times the natural logarithm of b, where b is some constant value which is positive and not equal to 1. Okay, that's it from me today. I hope you found this lesson useful. If you are struggling with anything, then please go back and watch the parts of the video that have confused you, or read about it in your book or online. All that's left is the worked examples, so same as normal. Pause the question, try and do the worked example on your own. If you get stuck, then look at the solutions, but you really should be trying as much as possible to do them on your own. Alright, good luck, and I'll see you tomorrow.
Davenport. 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 Davenport.